Okay, I want you to imagine something for a second. A computer that isn't built, but grown. One that literally heals itself, runs on almost no energy, and when it's done, well, it just returns to the Earth. It sounds like something straight out of science fiction, right? But as we're about to see, this living computer might be way closer than we think, all thanks to the hidden world of mycelium.
You know, for decades, silicon has been king. It's the engine of all our progress. But we're hitting a wall, a physical limit, and we're facing totally unsustainable energy demands and a literal mountain of electronic waste. So the question is, what's next? What if the answer isn't something we have to cook up in a sterile lab? What if it's something nature has already spent, about 1 billion years perfecting?
So this is kind of the choice we're looking at, right? On one side, you've got our current path, sucking up massive amounts of energy, creating toxic e-waste, and dealing with incredibly fragile, expensive systems. And on the other side, nature's model. Radically sustainable, completely biodegradable, inherently stable, and this is the craziest part, it builds itself.
All right, so to really get why a living computer isn't just some, cool party trick, we gotta talk about the crisis that's brewing in our digital world. The future of computing, especially quantum, is kind of balanced on a knife's edge, facing these huge technical and environmental problems. And that, my friends, is where our story literally goes underground. The potential solution has been right under our feet this whole time, quietly building one of the most complex and resilient networks on the entire planet. It's time to meet nature's secret computer, mycelium. So, what even is mycelium? Well, if you think of a mushroom as the fruit, mycelium is the tree. It's this enormous hidden network of tiny fungal threads. People call it the Wood Wide Web, and for good reason. It's basically nature's original internet, shuttling nutrients and information through the soil with incredible efficiency. And get this network is like it was made for computation. Its fractal, branching design isn't random. It's a super optimized system for being resilient and efficient. And the best part? It's completely sustainable. You can grow it pretty much anywhere, and its environmental footprint is up to 100 times smaller than the electronics it could one day replace. I mean, think about that.
So, how do we take all these amazing natural talents and turn them into actual processing power? Well, the first idea is absolutely audacious. What if we could use this living network to build the holy grail of computing, a stable, scalable quantum chip?
Okay, so first, a super quick refresher on what makes quantum so special. A regular computer bit is simple. It's on or it's off, a 1 or a 0. But a quantum bit, or a qubit, can be a 1, a 0, or, and here's the magic, both at the same time. And that single weird little difference is where all of a quantum computer's unimaginable power comes from. But, of course, there's a huge catch. That both at once state is unbelievably fragile. I mean, the slightest little thing, a stray vibration, a tiny shift in temperature, and poof, the whole quantum state just collapses. This is called decoherence, and it is the single biggest problem stopping us from building really powerful quantum computers. And this is where mycelium comes in with this incredibly elegant biological solution. So what happens is, the fungus just soaks up these tiny metal nanoparticles from its environment, and then it self-assembles them into perfect little quantum dots. You know, the building blocks of qubits. Then, the network wraps around these dots, acting like a living biological shield, protecting them from the exact things that cause decoherence. It literally grows a stable quantum system from the ground up. And that self-healing thing, that's absolutely key. Because the network has so many redundant paths, if one path gets damaged, no big deal. The information just finds another way around. In computer terms, that's a built-in living error correction system, something our engineers spend billions trying to create from scratch.
Okay, but how accurate could this possibly be, right? Well, in quantum computing, accuracy is called fidelity. And theoretical models suggest these mycelial quantum gates could reach fidelities over 99.9%. To put that in perspective, that's on par with some of the absolute best, most expensive systems we've ever built. But this one, it's grown, sustainably, at room temperature.
I mean, a self-assembling quantum computer, that's already a total game changer, right? But believe it or not, that's only half the story. It turns out this exact same living network could power a totally different kind of computing, one that runs not on electricity, but on heat.
So, we've seen how its crazy quantum properties could be put to work. But what if we used its simple, physical structure to compute in a totally different way?
This wild idea is called thermodynamic computing. Instead of using electricity to flip bits, you're using the flow of heat itself. Think about it, doing calculations just by making little patterns of hot and cold. It's a method that promises some absolutely radical energy efficiency.
And guess what? Mycelium just happens to be the perfect medium for this. Its fractal design is a natural heat sink, letting you create and control these complex heat patterns. In theory, this could let us build circuits that operate at the absolute physical limit of efficiency, a hard physical limit known as Landauer's principle. We're talking about the bare minimum energy needed to compute anything.
The potential density here is it's mind-boggling. Because it grows in 3 dimensions, researchers figure you could pack over 100 million thermal logic gates into a single cubic centimeter. That is a supercomputer in something the size of a sugar cube. And the best part? It's all powered by waste heat.
Okay, this all sounds pretty incredible, I know, and it's important to remember we're still in the early days. So what's the actual path from this amazing theory to a real, living, breathing computer? How do we actually start building on this fungal frontier?
Well, the roadmap forward is actually pretty methodical. First, you gotta see the network, right? So you use nanoscale imaging. Then you zap it with lasers to test its quantum properties. The next step is controlling it, using microfluidics to guide its growth with heat and nutrients, and maybe even using genetic engineering to optimize it. And finally, you build the bridge, hybrid systems that connect these living circuits to our electronics.
And look, this isn't just some abstract, far-off idea. Researchers are working with fungi you might have even heard of, like oyster mushrooms and reishi. This whole vision is grounded in real, living things that you can actually find out in the world. You know, when you really step back, this is about way more than just new hardware. It's a huge shift in philosophy. It's not just about building a faster machine. It's about learning to work with nature, to co-create with it, and design technology that actually integrates with biology for a future that's truly sustainable.
And all this leaves us with one last really fascinating question to chew on. As we explore this fungal frontier, are we really inventing something new? Or are we just finally starting to understand the language of a powerful, natural computer that's been running silently, efficiently, right under our feet for eons? It's a question that could change not just our technology, but our entire relationship with the living world around us.